This exam officially starts in the middle of chapter 6. Last exam did have, for example, a proof, I believe, of this property using a subgroup test that a direct image of a subgroup is a subgroup. And I also think talked about it in class and gave you maybe a homework problem where you did the inverse image. Actually, we're going to see today that this is a subgroup of G even when the phi function is what's called a homomorphism. It's operation preserving, but not necessarily one-to-one onto. This is still true. This set is still a subgroup of G, even if phi inverse as a function doesn't exist. This notation is still used. Okay, so that's something that I'll maybe highlight. Maybe today, maybe next Wednesday, I'll re-highlight it again. So we talk some about homomorphisms. It is something you should know, and it is actually helpful for real analysis. This is one idea that's really helpful in real analysis next fall. The idea of an inverse image, or pre-image is actually the word I prefer using, is a big deal in real analysis when you talk about continuity of functions, surprisingly. We've used these facts quite a bit. They're pretty intuitive. They're convenient ways of showing groups are not isomorphic. It's usually easier to show groups are not isomorphic than to show they are isomorphic. If they have different orders, they're not isomorphic. If one's cyclic and one's not, then they're not isomorphic. If one's abelian and one's not, then they're not isomorphic. If the largest order of element of G is not the same as the largest order of an element of G bar, then they're not isomorphic. Number of elements of specific orders, if it's different, they're not isomorphic. Those are examples of things that easily help you show things are not isomorphic. That could come up on the test. Then we got into automorphisms and inner automorphisms. That's certainly something you should know. And in fact, I am going to talk about those things more today with an example. Maybe not right now, but you should certainly know what an automorphism is. It's an isomorphism from a group to itself. Inner automorphisms are special automorphisms. They're sort of the only automorphisms that we're really used to, in a sense. They're the ones that have formulas. You might wonder, well, how could you come up with an automorphism without a formula? Maybe that's not so clear, but evidently it must be possible. In some circumstances, at least. But these inner automorphisms have formulas. For any fixed A, you can come up with this inner automorphism formula to define a function that is an automorphism G to itself. Though you do need to be wary, different A's could actually result in the same inner automorphism. That's emphasized in the book in at least one of the examples. Yeah, like this example. The group of inner automorphisms of D4. D4, remember, has 8 elements. It's the symmetries of a square. 4 reflections and 4 rotations. However, the group of inner automorphisms actually only has 4 elements. What they're talking about here is that these things essentially come in pairs. For example, R180 is the same as R0. Or phi sub R180 is the same as phi sub R0. Phi sub R270 is the same as phi sub R90. Phi sub H is the same as phi sub V. Phi sub D is the same as phi sub D prime. So it could be the same function even if the A is different. It's a fact you should know. Probably most just for sake of memorization. It's a particular group of automorphisms. The group of automorphisms of Zn is isomorphic to U of n. Cayley's theorem is technically, you could say, important. We've never really used it. It's sort of important from a big picture perspective that every group is isomorphic to a group of permutations. What that really means from a big picture perspective is that if you were only studying permutation groups in this class, if that's all we studied, we would be doing group theory completely, because all groups could be thought of as groups of permutations. The proof of that's kind of abstract, but I think worth studying because we encounter lots of abstract proofs like this. And so if you can conquer this kind of proof, understand it, it helps you with those other kinds of abstract proofs. I probably won't put this on the test, but it can be helpful for understanding abstract proofs. Chapter 7, we got into Lagrange's theorem. Certainly you should know, well, the definition of a coset. Actually, in this definition, H doesn't have to be a subgroup of G. You can still create these sets ah and ha and aha. However, almost never do people do that. Almost always H is a subgroup, and then you call it a left coset and a right coset. They don't give a name to this thing, but it's typically called the conjugate of H by A. And this is related to normal subgroups. Remember, when H is normal, this is going to be a subset of H. In fact, it'll equal H, and that's one of the properties that we have here related to normality. This lemma, I don't know if you went back to look at this since we've talked about normal subgroups, but property 8 is related to normality. Left coset of H in A, G containing A equals the right coset of H in G containing A, if and only if H is equal to the conjugate. It's not saying H is normal here. It's giving a condition under which the left and right cosets are the same. When this is true for all values of A, for all A in the group, that would be equivalent to normality. The definition of normal subgroup was that left cosets equal right cosets no matter what A is. This is related to the normal subgroup test. If this is true no matter what A is, then H is normal as well. But in this particular lemma, there's nothing about this being true for all A. It's just saying if this is true for a particular A, then this is also true, and vice versa. I hope you look over this list of properties and you feel like you've worked at cosets enough by now that these feel almost intuitive. Like, oh yeah, I remember that, or oh yeah, that seems right. Those kinds of thoughts should be in your mind as you look over these things. If they're not, keep working at it over Easter. Keep working at trying to think about these things with examples and also maybe with proofs. By the way, I haven't maybe emphasized this enough, though I think I did in the lectures. Property 2, AH equals H if and only if A is in H. That's a big deal, actually. You can, H will suck A into itself, so to speak. AH equals H. It's like the A is getting sucked into H, and you can make a slurping sound. If and only if A itself is in H. So in some of the proofs in the book, that property is used a lot, kind of without telling you. And you might be reading the proof and like, why is that true? Oftentimes it's this property. I think one example where that comes up is maybe in showing factor group multiplication is well defined. Let me just glance there quick. Yeah, here's the theorem that factor group multiplication is well defined. AH times BH equaling ABH is a group operation in the factor group. And you got to show it's well defined. And the reason is because the same coset can have different representatives. If you use A or A prime for this coset, or B prime for this coset, do you get the same thing in the end? Are these cosets the same? That's a big deal, showing things are well defined, that it makes sense. And the verification is based on normality and also uses properties of cosets. For example, when you look at this line right here, which is the key line, going from here to here, for example, that step right there, what's the reason for that? The reason is the H2 is getting sucked into H. That's why. Because it's in H. Sucked into H. That lemma that we were just looking at a minute ago is the reason for that step. Does it come up again? Yeah, I'm going from here to here, right there. The H1 gets sucked into H. Where's normality used? It's used a couple spots. That equality right there. Notice the BH becomes an HB. The left coset becomes a right coset. And also that equality right there, the HB becomes a BH. Technically, the author is being a little bit loosey-goosey in not putting extra sets of parentheses, but the author is assuming you realize to make this fully rigorous, you'd want to use associativity effectively of cosets, which is also a property here. Number 3. When you use associativity, you often use it without explicitly saying, hey, I'm using associativity, and oftentimes without explicitly using parentheses either. But it's there. That's a property. You should work at knowing these well enough that you could use them whenever you need to and identify what's true and what's not in a true, false, or multiple choice. Any of these proofs, could they show up on the test? Yeah, they're possible, I think.
For the associativity property, could you switch like H and B in the second part, like just switch H with anything? I don't see it really moving much.
Right, you mean right there?
Yeah. Can I
So
switch it?
the H and the B around?
Yeah.
Only if it's true, which is not always the case. It would be the case if H is normal.
Oh.
That's when left cosets always equal right cosets. When you got the element on the left, that's called the left coset. When you got the element on the right, that's called the right coset. BH is a left coset. HA right there, that's a right coset. Yeah. In factor groups, just as a convention, we always work with left cosets. But you could work with right cosets because they're the same thing when H is normal. Yeah, today we are reviewing for the exam, is starting to review, but we're going to review more next Wednesday because that'll be a week from now. Highlighting things you should make sure you know and memorize at least. Lagrange's theorem. That's the fundamental theorem of finite group theory. Most important theorem in finite group theory. Most foundational theorem. If G is a finite group and H is a subgroup, then the order of H divides the order of G. Also, the number of distinct left cosets, also right cosets, is this fraction, the order of G divided by the order of H. That's called the index of H and G. It's also the size of the factor group. That's not stated here, that this is the size of the factor group, because this chapter is not about factor groups yet. But we know later that factor groups are made up of cosets. The elements are cosets. So that is the size of the factor group. This theorem applies to finite groups. You can think about factor groups with infinite groups. It's possible that G and H are both infinite, but the factor group is finite. That's actually possible. There's a simple example of that. Z is, of course, is an infinite group. And here's a subgroup, cyclic subgroup generated by 2 in Z. That consists of all multiples of 2, right? That's also an infinite group under addition. It's a subgroup of Z. In fact, you could say it's a normal subgroup of Z because Z is abelian. But the factor group, this is worth writing down. The factor group has got finitely many elements. The factor group consists of all left cosets, and there's really only 2 of them. 0 plus the subgroup, which is the same as the subgroup itself, and 1 plus the subgroup. That's a 2-element group. Why are there no others? Because any other left coset you could make with any other representative is the same as one of these 2. For example, 2 plus this. Notice I am using addition here for my cosets because the group operation's addition. That consists of taking everything in this subgroup and adding 2 to it. And if I keep consistent with what I wrote down in there, I write it that way perhaps, but that really is the same set. And in fact, any even number in front will give you the same set, which is the identity of the factor group. Any odd number in front will give you the same thing as the other element of the factor group, 1 plus the subgroup, etc. You're never going to get anything different. So this is a 2-element group. It's isomorphic, in fact, to Z2. In general, in fact, you can say that Z modded by the factor group of Z by the cyclic subgroup generated by N is in fact isomorphic to Zn. I'll re-emphasize this probably later today or next Wednesday using homomorphisms. Re-emphasize this exact same fact either later today or next Wednesday.
It's going to be a really basic section, but how do you know, just because it has 2 elements, that it's going to be isomorphic to Z2?
Because I've mentioned that before. Any group with 2 elements is isomorphic to Z2.
But if they have like 6 elements, it's not necessarily going to be isomorphic to Z6.
Right. Right. What classification facts do we know so far? One big one is a consequence of Lagrange's theorem. In fact, in chapter 7, we start the classification facts. The first one is a corollary of Lagrange's theorem. Every group of prime order is isomorphic to ZP. So any group of order 2 is isomorphic to Z2. Any group of order 3 is isomorphic to Z3. 5 is isomorphic to Z5. 7 is isomorphic to Z7. Jump to 11 is isomorphic to Z11. Groups of prime order, up to isomorphism, there's only one. They have to be cyclic groups. That includes a lot of examples, infinitely many, but there's also infinitely many examples that it does not include. Group of non-prime order would not fit into this. But we do have other classification facts. Theorem 7.3 says if G has order 2p where p is a prime greater than 2, then there's 2 possibilities. It's either cyclic, isomorphic to Z2p, or dihedral, isomorphic to dp. dp would have order 2p. We use the subscript p there, if it was never clear to you before, to emphasize the number of sides of the polygon it's a group of symmetries for. So, D4 is a group of symmetries of a square, and squares have 4 sides. But D4 itself has 8 elements. D3 is a group of symmetries of an equilateral triangle, but D3 itself has 6 elements. D5 would be the group of symmetries of a pentagon or regular pentagon. The sides have to be the same length and the angles have to be congruent. But it's got 10 elements. So you've got 2 possibilities here. This does include the case where the order is 6, like you were just asking about, Caden. If the order is 6, 6 is 2 times 3. P is 3. That fits this. It's isomorphic to Z6 or D3. Wait a minute. What about S3? S3, right? Symmetric group has 3 factorial, 6 elements. That's another group of order 6. This theorem is saying it's got to be isomorphic to one of those. Can't be this one because S3 is not abelian. So it's got to be this one. The group of symmetries, the symmetric group S3 is isomorphic to the group of symmetries of an equilateral triangle. Which does make some sense if you think about it pictorially. If you label these 1, 2, 3, and you think in terms of, for example, a rotation by 120 degrees, doing that, you could think of that in terms of a permutation. There was one class period like about a month ago where we talked about that. I think I tried it with squares, but I was mistaken in how I was thinking about the permutations. I made mistakes. The better way to think of it here is that effectively one's getting mapped to 2 because 1 goes there, 2 is getting mapped to 3 because 2 goes there, and 3 is getting mapped to 1. R 120 effectively equals, in quotes, the permutation 1, 2, 3. And any other kind of symmetry of the equilateral triangle could also be thought of as permutation, as another example. If we flip about the vertical line of symmetry, call it V here, 3 and 2 get swapped, but 1 stays where it is. So V is effectively the cycle 2, 3. That's hinting at S3 being isomorphic to D3. But S4 is not isomorphic to D4. Got to be careful. This only works with S3 and D3. S4's got 24 elements. D4's got 8 elements. There's a subgroup of S4 that's isomorphic to D4, but not all of S4. Not every symmetry of a square. Well, not every permutation in S4 is realizable as a symmetry of a square. S4 would have 24 elements, 4 factorial. D4 has 8 elements. You should know the definition of a stabilizer in an orbit and know the orbit stabilizer theorem. And I also said you should know the proof of the orbit stabilizer theorem. I think I have sometimes put the entire proof on tests, but perhaps more likely I'm sort of in more recent years been defaulting towards shorter proofs on tests. Maybe I'd be more likely to have you prove part of it. And I try to specify exactly what I mean when I say part of it, if I put it on the test. For example, showing this function t is well-defined. That's a big deal, right? I already said well-defined is a big deal today. You don't need to memorize that thing. I mean, it's interesting. The group of rotations of a cube is isomorphic to S4. Talking about a cube, a 3-dimensional object, right? The group of rotations, not reflections. You're just thinking about rotations. It's isomorphic to S4. That's kind of interesting, but it's not something that you need to know for the test. It's an application of the orbit stabilizer theorem. Let's spend our last 25 minutes highlighting as much as we can about chapter 10 to help prep you for the exam on group homomorphisms. So we'll go through some definitions and theorems. We'll also look at some examples, try to really get the key ideas across that you should know for the test. First of all, the definition of a group homomorphism. A homomorphism phi from G to G bar, where G and G bar are groups, is a mapping from G to G bar that is operation preserved. Phi of AB equals phi of A times phi of B for all A, B, and G. Realize, as we've emphasized before, if the group operation is addition, you should write this with addition symbols. And actually, the operations in G and G bar could be different. Maybe you use addition with one of the operations, but not the other. There are different forms of this. It could look like this. If the operation in both G and G bar are addition, it could look like this. If the operation in G is multiplication, but the operation in G bar is addition, or it could look like this. If the operation in G is addition and the operation in G bar is multiplication. The form of the operation, whether it's addition or multiplication, for purposes of groups and whether they're isomorphic to each other, for example, is irrelevant, right? You could have a multiplicative group and an additive group be isomorphic. As a simple example, say you had an element in a group of order 2, an arbitrary abstract group, the cyclic subgroup generated by that element would be those two elements, the operation would be multiplication, but it would be isomorphic to Z2, whose elements are 0 and 1, where the operation is addition, mod 2. So the form of the elements and the form of the operations themselves, for purposes of classification, and whether two groups are isomorphic or not, is irrelevant. But again, with homomorphisms, you are just after them being operation preserving, nothing about them being one-to-one and or onto. They could be neither one-to-one nor onto. In fact, you should know that if you got any group and the arbitrary abstract trivial group, you can define a homomorphism from that group to the trivial group, map everything to the element E. Maybe I should call it E bar instead of E. That's a homomorphism. It's operation preserving. Phi of AB would be E bar, and phi of A, phi of B would be E bar times E bar, which is E bar. It's called the trivial homomorphism. And it's definitely, if G is non-trivial, it's definitely not one-to-one, and it's definitely not, well, okay, it is onto, but it's definitely not one-to-one. And you can come up definitely with homomorphisms that are not onto either. In fact, if you thought of this as a mapping to G bar instead, where G bar was bigger than just E bar, then it would not be onto. The kernel of a homomorphism is everything that gets mapped to the identity. E. In, well, it probably would have been better for the author to call it E bar. E bar in G bar. All the elements of G such that phi of X equals, again, it would have been better if the author wrote it E bar to be consistent with the notation here. That's the kernel of the mapping, the homomorphism. I have emphasized that we know about kernels from linear algebra as well, and you should know that. Should maybe even be able to find the kernel. It's the same as a null space of a matrix. Do row operations, identify free variables, write the solution set in parametric form, vector form. In all those kinds of problems you did in linear algebra, you were finding kernels using matrices. Yes, isomorphisms are homomorphisms that are also one-to-one and onto. Some more examples are here. Maybe this one's worth highlighting. This is going to come up in ring theory. Let R of X with square brackets around the X denote the group of all polynomials with real coefficients, where the group operation is addition. So the elements here in this group are polynomials. We haven't talked about this group before, but I'm talking about it right now. Define a mapping really from R of X to itself, where you map every polynomial in R of X to its derivative. That F prime there is not an arbitrary symbol F prime, it's the derivative of F. From calculus. That is a group homomorphism. Why? Well, first of all, R of X is a group under addition. Under addition, I'm adding the polynomials by adding like terms. I'm not multiplying them here. It's an infinite group under addition. Why? Well, if you add two polynomials, you get another polynomial. It's closed. Polynomial addition is associative. There is an identity polynomial under addition. It's the polynomial 0. Constant polynomial whose graph is the horizontal axis, if I asked you to graph it. And every polynomial F has an additive inverse, negative F, where you negate all the coefficients of F. This is a group homomorphism. Why? Because we know from calculus that the derivative of sum is the sum of the derivatives. That's a calculus fact. that we know is true. We don't have to reprove it. That's calculus. How do we prove it in calculus? You got to use limits, but we're not getting into limits. We're just trusting the calculus. What's the kernel of this mapping? It is a homomorphism. This proves it's a homomorphism. Notice the plus sign, the operations addition. What's the kernel? It's everything that maps to the identity. What's the identity? 0. The polynomial 0. So I'm after all functions whose derivative is always 0. The kernel is all constant functions that have a graph that's a horizontal line. Infinitely many such functions. The kernel is infinite. You could say the kernel of phi here is all, I'll just write it in words, all constant functions. Or constant polynomials if you prefer. Polynomials are functions. And constant functions are polynomials too. So it's okay to say constant functions. Okay, so there's a new example. It's a worthwhile example to emphasize even just today. It is an important example for ring and field theory, actually. The mapping from Z to Zn, where you map every number m to m mod n, is also homomorphism. That's based on properties of modular arithmetic. This is a kind of interesting example. Zi, that's called the Gaussian integers. I encourage you to read it. I'll tell you I won't test you on it because we got to rush here. But I will tell you that this example comes up in ring and field theory. So it's worthwhile to still study and think about. We have not really focused on internal direct products. I'm not going to focus on internal direct products in the exam, though if you did read about internal direct products, you could study this example. Here's an example that's not a homomorphism. Phi of x equals x squared from R to itself under addition is not a homomorphism because phi of A plus B is that, whereas phi of A plus phi of B is this, phi of B is this, and these are not equal when A and B are non-zero. Right, it's a common thing in pre-calculus sometimes for people to say A plus B squared, quantity squared is A squared plus B squared. They're not foiling. You know not to do that. However, I will say phi of x equals x squared is a group homomorphism when you're mapping R star to itself. What's R star? We talked about this before. It's R take away 0. It's a group under multiplication. The non-zero real numbers, I've said this before, does form a group under multiplication. You have to take out 0 because 0 doesn't have any multiplicative inverse. Can't divide by 0. 1 over 0 is undefined. Once you take out 0, what's left is a group under multiplication. In fact, an infinite abelian group, the identity is 1 because the operation is multiplication. And phi of x equals x squared is a group homomorphism here. Why? Because it's operation preserving. XY quantity squared is x squared times y squared. R star is abelian. But that's phi of x times phi of y. In fact, more generally, we can get even more general here, not just with the formula, but also with the group. A mapping phi from C star to itself, where C star is the complex numbers take away 0. It's a group under multiplication defined by phi of x equals x to the n power is also a group homomorphism. N is, in fact, any integer, even negative integers, I believe, work. Yeah, there's nothing about n having to be a positive integer here for this to work. And I'm not dividing by 0 when n is a negative integer because I'm excluding 0 from the group that I'm thinking about. And if, for example, n is 4, what's the kernel of this? It would be everything that maps to the identity. The identity is 1. We're looking for all solutions of x to the 4th equaling 1, which includes 1. It includes -1. It also includes I and negative I. The kernel is 1, -1, I, and negative I, right? Because I squared is -1, so I to the 4th would be -1 squared is +1. And the same kind of thing happens with negative I. Saying these examples, these are new, but you really should be able to think these through with a little bit of help. I mean, finding like 8th roots of 1, that's getting harder, but this is a simpler one. Should know the properties of homomorphisms. Just like isomorphisms, they carry the identity of G to the identity of G bar. That happened with isomorphisms too. That's not surprising. Isomorphisms are homomorphisms. So if it's true for homomorphisms, it's got to be true for isomorphisms. We did prove this one day, and the proof didn't involve using, well, we did one proof using onto, but we also did a proof that did not use onto when we proved it for isomorphisms. Phi of G to the n is phi of G to the n. The book forgot a parenthesis there, typo. Here's something a little different though. With isomorphisms, the order of G matched the order of phi of G. But with homomorphisms, the order of phi of G might be less than the order of G. As a trivial example, consider that one. The order of phi of G is 1 no matter what G is when you're mapping everything to the identity. So with homomorphisms, the order can go down. It can't go up, but it can go down. But you can say more. If the order of G is finite, then the order of its image divides the order of G itself. And if the order of capital G is finite, then the order of the image not only divides the order of little g, but also the order of the direct image of capital G. And if phi happened to be onto, that would be the same as the order of G bar. Kernel is a subgroup. It's also a normal subgroup, in fact, though it's not stated there. I think that might come up on the next page. Kernel is a subgroup. You should be able to use the subgroup test to prove that. Is a normal subgroup test. You should be able to use the normal subgroup test to prove that. Pretty important fact. Which I'll re-emphasize in a few minutes here. These are important too, and in fact, these are helpful for solving that exam problem, one of these at least. Phi of A equals phi of B if and only if the left cosets of the kernel in G containing A and B are the same. So imagine with me, you got G here, and you got G bar over here. There's E bar. Everything in the kernel, pretend the kernel is right here, gets mapped to E bar. Other cosets, like this one, say A curve phi, everything in there, what that fact we just looked at implies is they all get mapped to one thing. Call it phi of A. You got another coset representative, B, for this coset, that theorem, that part of that theorem says phi of A equals phi of B. And that's true for all the cosets over here. Homomorphisms collapse cosets of the kernel to individual points over here. That's important intuition. Related to that, if phi of G equals G prime, maybe the book should have used G bar instead of G prime. The preimage, remember preimages? Preimage of G prime, it's a little different than we talked about preimages before. We talked about preimages of subgroups before. G prime by itself is not a subgroup of G bar. Everything in G that maps to G prime is the coset that contains G, where G maps to G prime. Got an element over here. Okay, I'll call it G prime, where phi of G is G prime. So this G gets mapped to G prime there. The preimage of G prime, in other words, everything over here that maps to G prime is that coset. G cur phi. Everything in there maps to G prime. Again, essential. This is essential intuition for homomorphisms. You want to work at here still between now and Friday. I claim this is helpful for solving problems too. Let's look at that problem. Let phi be an element of odd of Z. Think about what that means. That means phi is an isomorphism from odd of Z9. Phi is an isomorphism from Z9 to itself. Actually, that fact that we were just looking at is not helpful for this. I was mistaken. But we can still try to solve this problem anyway. We'll come back to it. We'll come back to it. We should still focus on some other things here. More properties of homomorphisms. Effectively, homomorphisms take your group and they sort of construct a simplified version of the group, in a sense. The direct image of a subgroup, for example, is typically simpler, you might say, than the subgroup itself. But if the subgroup is cyclic, then so is its direct image. If the subgroup is abelian, so is its direct image. If it's normal, so is its direct image. That's something you could prove with the normal subgroup test, and you should be able to for the test. If the kernel has n elements, then it's an n-to-1 mapping. Effectively, what I just showed you here with this picture is a visual demonstration of that fact. Just imagine the kernel to have n elements in it. Remember, cosets have the same number of elements, distinct cosets. If H is finite, then the order of the image divides the order of the original H. Let's jump ahead. Pre-images of the normal subgroups are normal subgroups. You should be able to use the normal subgroup test to prove that. If phi is onto and the kernel is trivial, then it's actually an isomorphism. So effectively, the kernel being trivial means this is 1-to-1. That came up in linear algebra. You got trivial kernels when there are no free variables. Your linear transformation was 1-to-1. It's all related. Before we look at that problem, let me just highlight the first isomorphism theorem. Okay, I talk about this in the lecture. You should know it for the test. Watch the lecture, okay? If you haven't been watching lectures recently, watch this one. Okay, I talk about this in depth, including proving it, including the proof involving the well-defined issue, which I've tried to make a big deal of in various contexts. Let phi be a group homomorphism from G to G bar. Then the mapping from this factor group, notice the kernel is a normal subgroup, so you can make the factor group, to the direct image, given by taking an arbitrary coset and mapping it to the image of G under phi, is an isomorphism. Isomorphism. It's 1-to-1 and onto as well as operation preserving. In symbols, this factor group is isomorphic to that direct image. And notice also this means that if phi is onto, you could replace phi of G with G bar. This is a big deal. I don't have time to make much of this right now, but it's a big deal. So watch the lectures. and its corollaries. Let's finish by just looking at this problem. If you've got an automorphism of Z9, meaning an isomorphism from Z9 to itself, suppose phi of 4 equals 2, find phi of 7. With a hint. 4 is a generator of Z9 and phi is operation preserving because we're assuming it's an automorphism. Okay. Phi of 4 equals 7. Is that what it said? Phi of 4 equals 2, excuse me. What is phi of 7? Phi is mapping, phi is an element of odd of Z9. So phi is a mapping from Z9 to itself that is 1-to-1 onto an operation preserving. The group operation in Z9 is addition mod n. I gave a hint, 4 is a generator for Z9. Think about that. Cyclic subgroup generated by 4 is 4. 4 plus 4 is 8. 4 plus 4 plus 4 is 12. Mod 9 is 3. Add another 4 gets 7. Oh, yeah, 7 is 4 added to itself 4 times. Maybe we can stop there. Okay, for completion, I'll keep going. But 7 is 4 plus 4 plus 4 plus 4, mod 9. Phi is an operation preserving. What is phi of 7? Well, since 7 is 4 plus 4 plus 4 plus 4, and phi is operation preserving, you can write this. The group operation is addition. We're assuming phi of 4 is 2, so we get 2 plus 2 plus 2 plus 2, which is 8. Mod 9 is still 8. So the answer is that phi of 7 is 8.